Hi guys, today we'll see the graphical representation in memory. So we have seen what is meant by a graph and what are the different types of graphs we have seen. Now the next concept we will see is how the graph can be represented in the memory. So graph can be represented in memory different ways. The first one we will see is a adjacency matrix. So the mathematical notation for the graph is it is G equal to order pair V comma E. V is set of vertices and E is set of edges. Let us assume now this is a graph you have and it is an undirected graph. If you observe, we don't have any directions here. It is an undirected graph and you have weights also. Weights are also assigned. So it is an undirected weighted graph. Now for this, let us see how you can represent in the memory. It is the first method you have is a adjacency matrix. So adjacency matrix is a square matrix. So what does a matrix consist of? It consists of rows and columns. Now if you observe how many vertices you have here, 5 vertices you have. That means you will be having 5 rows and 5 columns. If you have an edge, you will be representing with 1. If you don't have an edge, you will be representing with 0. Now come here, 1, 1. Do you have an edge from 1 to 1? No. So it is 0. Do you have an edge from 1 to 2? Yes, you have an edge from 1 to 2. It is 1. 1 to 3, do we have an edge? No, we don't have an edge from 1 to 3. It is 0. Do 1, 4. Do we have an edge? Yes, we have an edge. 1. Do we have an edge from 1 to 5? No, so it is 0. So, in this way you are filling. If you have an edge, it is 1. If you don't have an edge, it is 0. Since the number of vertices are 5, the size of the matrix is a 5 by 5. So, this is the definition I gave. A of ij equal to 1 if I and j are adjacent. Adjacent means if there is an edge between the vertex I to vertex j, then it is 1, otherwise it is 0. So this is one way of representation of a graph in the memory. That is, the first one is a adjacency matrix. Now the second one we have is a adjacency list. So adjacency list. So the same example again I am showing here. How many vertices you have? 5 vertices you have. 5 vertices you have. Now this adjacency list you will be representing with the help of a linked list here. Now if you see for 1, what are the adjacent vertices for 1? Adjacent vertices for 1 are 2 and 4. 2 and 4 are the adjacent vertices. So, the 1 adjacent vertices are 2 and 4. Now, coming to 2. What are the 2 adjacent vertices you have? We have 1, 3 and 4. 3, 4. Now, coming to 3. What are the adjacent vertices of 3? 2, 4, 5. 2, 4, 5. You are representing with the help of a linked list. Now, 4 adjacent vertices, 1, 2, 3. 1, 2, 3. And 5 also. 5. Now, coming to 5. 5 adjacent vertices are 3 and 4. 4. So, this is an adjacency list for this particular graph. Now I have shown you two ways. One is adjacency matrix and other one is a adjacency list. So here we can use the dense graph for a matrix. If you have a dense graph, we can use a matrix notation. If you have a sparse, then we can go with the adjacency list. The meaning is dense graph is nothing but we can take an example for a complete graph. What is meant by a complete graph? If one vertex is connected to all the remaining vertices, that we call it as a complete graph. So in the case of dense graph is nothing but the example for a dense graph is a complete graph. So if you are having a complete graph, better we go with the representation of a adjacency matrix. If it is a sparse matrix is we don't have a connection from one edge to all the vertices. For example, for 1, we don't have the connection to all. In that case, we can go with the adjacency list. Now, the other way of representation we have is a set representation. So, set representation, What is the mathematical notation? You have G equal to V comma E, order pair V comma E. So V is a set of vertices and E is a set of edges. So that is the thing we are showing here. V is the vertex list. What are the vertices you have? 1, 2, 3, 4, 5. V vertex set and edge. Edges what you have? 1, 2 we have. Next we have 1, 4, 2, 3. So all the edges we are writing here. And for example, if it is a weighted graph, if you see it is a weighted graph here, then we have to include the weight also. So 1, 2 and 7. So 1 becomes the vertex, these two are the vertices and this 7 becomes the weight here. The meaning is between 1 to 2, we have the weight is 7. Similarly 1, 4. 1, 4, what is the weight you have? 1. So this is the way you will represent. Now the same adjacency list for a directed graph. This is a directed graph you have. Now for the directed graph, the adjacency list. How many vertices you have? 4. A, B, C, D are the 4 vertices you have. Now again we are representing with the single linked list here. So if you observe, for A, what are the adjacent vertices you have? It is C you have, and here it is a weight. The weight you are representing with the 3. Here we are taking 3 parts we have. The first part is representing the weight and the second one is a node, and this is representing what you have to the next, that adjacent node here. So for A to A we don't have, so that is the reason we have taken null here. The adjacent vertices of A is C. And what is the weight you have from A to C? It is 3. Now coming to B, the adjacent vertices of B are A, C, AC and D also you have, A, C and D. So from B to A, B to C, how much you have? It is 1. B to C, it is 1. Again, B to A, it is 5. B to D, it is 7. So, now coming to C. C adjacent vertex is A and D. A and D. So what is the weight you have? 2 and another one you have is 4. Now the D adjacent you have is B you have. Sorry, something I missed here. This should be B. And another one we have is, one second. For D, the adjacent vertex you have is B. Only B we have. Do we have any other thing? No. This is the thing you have. Now, if adjacency matrix is given, from the adjacency matrix, we have to find out the adjacency list here. And one more thing is, if it is an undirected graph, the adjacency matrix will be symmetric. If it is an undirected graph, it is symmetric. What is my symmetric? A transpose is equal to A is symmetric. A transpose is equal to A. If it is satisfying, it is symmetric. So for undirected graph, this property will be satisfying. So for undirected graph, it will be symmetric. But for a directed graph, it will not be symmetric. It may or may not be. So here if you observe, this is the thing you have. And if you observe the diagonal, the upper triangular and the lower triangular we have same. And if you find out the transpose, it will be same. A transpose is equal to A. So it is a symmetric matrix here. Now for this, let us see the adjacency list here. So how many vertices you have? 0, 1, 2, 3 are the vertices you have. And since it is a symmetric matrix, it is just enough to check the upper triangular. Again, no need to check the lower triangle here. Now I am starting with the 0. Here we have 1. Here we have 1 means the meaning is you have an edge from 0 to 1, 0 to 2 and 0 to 3. If you have a 1, it is edge. So what are the adjacent vertices of 0 now? 1, 2, 3. Now coming to 1. What are the adjacent vertices? Here you have 1, 1. That means adjacent vertices of 1 are 2 and 3. Sorry, here also you have 1. So here the adjacent vertices are 0, 2 and 3. 0, 2 and 3. Now adjacent vertices of 2 are 0, 1, 3, 0, 1, 3. And adjacent vertices of 3 are 0, 1, 2, 0, 1, 2. So from the adjacency matrix, we are finding out the adjacency list here. Okay. Now we will see the another way of representation. Yeah. Now we see the other way of representation. That representation you call it as an array representation. It's little difficult. Please listen carefully here. Now this is a graph which is given to us now. For this graph we have to go with the array representation. So how to do with the array representation is, first I will take the array here. Now initially I don't know what is the size and everything. Now 4 vertices you have, I will take 4 vertices, 1, 2, 3, 4 vertices we will take here. Now what I'll do here is, 4 vertices I have taken here, 4 vertices I have taken. Now I'll take here 5, 6, 7, 8, 9 and so on. Okay. Now coming to 1, what are the adjacent vertices of 1, 2, 3, 4? 2, 3, 4 are the adjacent vertices of 1. So that should be placed after 4. These are the 4 for the vertices. Okay, 4 vertices you have, 4 vertices. Now adjacent vertices of 1 are 2, 3, 4. So where I will be placing? I will be placing in the 5th place, 6th place and the 7th place I will be placing. The adjacent vertices of 1 I am placing in 2, 3, 4, where after this 4. So that means, from where did I start now? Sorry, a small mistake here I have done. I said we have 4 vertices. So 4 vertices we are considering, and the 5th vertex also we have to leave. So 4 vertices and one more place also I am leaving it here. That means up to 5 these are empty. Now we will start now. 1. What are the 1 adjacent vertices? 2, 3, 4 are the adjacent vertices. So you have to start after 5. So 2, 3 and 4. This is the way I have filled now. So now at 1 I should write, what I have to write for 1 is, what are the adjacent vertices of 1, 2, 3, 4. Where it is starting? It is starting from the vertex 6. It is starting from the vertex 6 here. Okay. I hope it is clear for you. Now coming to 2. 2. What are the adjacent vertices of 2? 1, 3, 4. So after this I will write down now 1, 3, 4. So where it is starting? It is starting at 9. This is 10 and 11. So it is starting at 9. That the meaning is, the 1 adjacent vertices are starting from 6. And here the meaning is 2 adjacent vertices are starting at 9. So this is the thing what I have written here. So 2 adjacent vertices are what? 1, 3, 4. So 1, 3, 4. Finished. Now come to 3. So these 2 we have done. And here we have done up to here. Now what are the 3 adjacent vertices? 1, 2, 4. 1 to 4. I am starting from 12. So 12. Now come to the 4. 4 adjacent vertices are 1, 2, 3. So here I am starting from 15. 15. 15. So where it is stopping? At 17. Now here the 5th node, which one we are kept empty, which one we kept empty here, the extra thing we have considered, that should be the last. After 17 whatever we have, 18 we have to take. That means we are indicating the array has been ended. So this is the thing what you will get here. So for this example, n equal to 4, and how many edges we have? 6 edges you have. So in this case, what will be the array sizes? The array size is n plus 2e plus 1. What is n? 4 plus 2 into e. E is 6 plus 1. So it is how much? 17. So for this array, the array representation, the size of the array should be 17. Now, if you take this example, this is the adjacency matrix is given to us, and if you observe, it is a symmetric. It is a symmetric matrix we have. For this, let us go with the array representation. So take this matrix. This matrix here, and for the same matrix I have shown the adjacency list also. You can just check the adjacency list. And since it is symmetric, you can just check the upper triangle. Like I'll just show you one or two. Now, first one you have is 0. So 0, where do we have 1, 1? For 1 and 2. 1, 2. So this is adjacency list what we have. Now, let us take here the array. So how to take the array now? So how many we have? Total 8. 0 to 7 plus 1 is for extra. So up to 8. 8. Now what are the 0 adjacent? 2 and 1. 2 and 1. So where it is starting at? 9. So 9 it is starting. So 2, 1. This is completed for 0. Now come for 1. What are the adjacent vertices for 1? 3, 0. 3, 0. Where it is starting? It is starting at 11. So same for 2. It is 0 and 3. 0 and 3. Where it is starting? At 13. Now coming to next one. 3. It is 1 and 2. Where it is starting? It is starting at 15. Now for 4. It is 5. Where it is starting? At 17. Next, for 5, 6 and 4, where it is starting? 18. Now next, 6, 5 and 7, where it is starting? At 20. 20. Next, for 7, where it is starting? At 22. Now 8 will be the last, 23. So this is the thing. Now, what should be the size of the array now? What should be the size of array is n plus 2e plus 1. Nodes is nothing but the array name. This is array name n plus 2e plus 1. So n equal to 8. And how many edges you have? If the graph is given, then we can say how many edges we have. But the graph is not given. What is given is a matrix is given. So how to find out how many edges? And also, already I said it is a symmetric matrix. So it is an undirected. So you just consider the upper triangular. Upper triangular, if you consider how many ones you have, 1, 2, 3, 4, 5, 6, 7. 7 ones you have. That means E equal to 7. Equal to 7. And if you substitute, we are getting 23 locations. Yes, yeah, 23 locations, 0 to 22. That means 23 locations. So this is the way how we represent the adjacency matrix by using the adjacency list and by using the array. Thank you.